So the first law of thermodynamics allows us to calculate energy changes involving a chemical reaction, and it will tell us if a reaction, when it happens, will release heat or will absorb heat. And that's all well and good. But we actually have no idea if the reaction is going to happen or not. Nothing what we have discussed so far about enthalpy and energy release or being absorbed, it says without any doubt whether a reaction is going to happen. So one could think, okay, well, exothermic reactions will happen because the reagents have enough energy to produce the products and release some additional energy, and that's what we call them exothermic. So endothermic reactions, because the energy of the reagents does not have enough energy to make the products, those will not happen. And I would think, okay, well, that's okay. But it's actually not the case. Yes, exothermic reactions, because they have enough energy, the reagents to produce the products will happen spontaneously, but some endothermic reactions do happen spontaneously. Just the fact that the reaction is endothermic does not necessarily mean that it's not going to happen. And I'm having here a couple of examples. One is dissolving potassium chloride in water, and the other one is the decomposition of dinitrogen tetroxide to produce NO2 gas. These two reactions are endothermic. Positive enthalpy changes, the reactions need energy. However, they happen spontaneously. There is enough energy in the surroundings around those reactions for the reactions to happen spontaneously. So just defining enthalpy or internal energy, just with the first law of thermodynamics, we don't have enough to, just by looking at a number or by looking at the sign of a number, to say, oh, that reaction is going to be spontaneous, or that reaction is not going to be spontaneous. We need to introduce a new concept, and that new concept is called entropy. And a spontaneous process is a process that will happen in its own accord. I'm sorry, this should not be an apostrophe here. In its own accord, without the outside intervention. So, and it will be an irreversible process. It will happen. There will be a beginning, the reagents, they will make the products, and that's it. They stop there. And as I was saying, exothermic reactions, because the reagents have enough energy to produce the products, they can proceed spontaneously because they don't need any outside intervention. But some endothermic reactions, which, yes, you do need some input of energy in the system, but it's enough that it can be naturally given by the surroundings, are also spontaneous. So we introduced this new concept, entropy, and it measures, there are quite a few definitions, but it could be seen in a sort of more general, simpler terms as a measurement of randomness, a measurement of the disorder of the system, how disordered our system is. And so the greater the disorder it is, the more disorder, the more random our system is, the more dispersed it is, the greater the entropy. So we define entropy as a state, well, it's a state function. It depends on the initial and the final state. And we look again not at entropy absolute values, but entropy values, but the changes in entropy between the final state, the products, and the initial state, the reagents. And we look at entropy as a measure of how dispersed, how chaotic, how random, how disordered our system, our chemical reaction is. So what would be the molecular interpretation of entropy? Well, we will look at the molecules in our reagents and our products, and then we'll see what's happening with those molecules. Well, they will be moving in the solutions. They will be vibrating. The bonds will vibrate. They will be rotating. So those molecules of the reagents, and then when the reaction happens of the products, are not stationary. They are moving. They are moving all the time. They are rotating, and the bonds are vibrating. And all that energy involved in those processes of motion, translation, rotation, that is what we are measuring when you are measuring entropy. So if we imagine we have an ideal gas, we have a gas in a container, we have 1 mole at a particular temperature and in a container of a particular volume and whatever pressure. Imagine we take a snapshot, like little pictures of all the molecules of that gas trapped in that container. So we will be taking, if we have 1 mole of gas, we have 6.022 10 to the 23 molecules of the gas there, Avogadro's number, and in any time that we're taking this snapshot, they will be in a particular position doing something, and then we just kind of, it's like take a picture, and then we take a second picture, and then a second picture. We call all those kind of snapshots microstates. And if you imagine that over time, we have a staggering number of possible microstates, because the molecules are moving all the time, and they will all be different because this gas, the molecules are moving all the time, they are vibrating, and you have 1 mole of them. So 6.022 10 to the 23 molecules, all moving in that container. So we must use statistics. It's not something we can handle just with normal numbers. And we talk about microstates, and we talk about thermodynamics states, and we talk about the number of microstates that your mole of gas might have, and we call that number, that variable W. And well, you need the statistics, and you need something called Boltzmann constant, and then we can define the entropy as the number of microstates you can have, but the natural logarithm that you have, and times the natural logarithm of the microstates you have times k, which is Boltzmann constant. And well, how will they look? So if you go from a solid to a liquid, if you think of the changes between a solid in which the molecules are kind of attached to each other in intermolecular forces, and the liquid in you have broken some of those intermolecular forces, and the molecules are more free to move. When you move from a solid to a liquid, then you have an increased number of microstates. There are more possibilities of those molecules having moved from one snapshot to the next. When you increase the temperature of a system and you have a gas, if you're a solid or a liquid, maybe the changes in temperature, the molecules are sufficiently interacting with each other. Those intermolecular forces don't let them move too much. But if you have a gas and you increase the temperature, you are increasing the number of microstates, because you are giving energy to the system. You are giving those molecules kinetic energy, and they can move faster and they can move more. You have more microstates, so you have increased entropy. It has become more positive. If you increase the volume, and if you have a gas, if you have a solid, it has the volume it has, and if you just because you have it in a larger container doesn't make much difference. A liquid, the volume is quite fixed. There's very little change in volume. So yes, it will change the shape of the container, but just because you have a larger container doesn't mean that you're going to have a larger volume of liquid. But gases do. Gases tend to occupy the volume of whichever container you have them in. So if you increase the volume, then you're giving more space to all those molecules. They will be moving, and they can move in many other ways that before in a smaller volume they could. So you have increased the number of microstates. Therefore, you have increased the entropy of the system. So when you increase dispersion, when you leave the molecules more space to move, when you're breaking intermolecular forces, so the molecules are less tightly held together and they are more free they are freer to move more freely, or when you increase the volume so they have more space, they can disperse more. All these things that I've mentioned increase the dispersion of your system. There is more space for the molecules to move. There are fewer intermolecular forces for the molecules to move. You have increased the temperature, you have given them energy, they have more energy to move. All those changes increase the dispersion of the system, and they increase the entropy. They result in a positive entropy change from the beginning of whatever of the system to whatever change you have introduced to the final state. So, as a summary, entropy measures the tendency towards dispersal, the tendency towards disorder. The greater the dispersal, the more disordered the system is, the greater the entropy change. In a spontaneous change, sorry, this should not be a D, it should be a delta, the total entropy of the system and its surroundings must increase. So the change in entropy must be positive. So when you have an endothermic reaction, the change in enthalpy is positive. It means that the system does not have enough energy to make the products. The reagents don't have enough energy to make the product. You have to communicate that heat. So one would think, okay, well, it's not favorable because enthalpy is not favorable for the reagents don't have enough energy to make the product, so they wouldn't make them. But if the reaction itself involves an improvement in entropy, so the system you end up, the products you end up are more disordered than the reagents, and that may be in some cases sufficient to allow that changing entropy is positive and is large enough that the reaction will happen spontaneously. So in the two examples I gave you, enthalpy was positive, the reaction was endothermic, the reagents themselves did not have enough energy to make the product, but the products ended up with a more disordered state with respect to the reagents. In the first case, we have the solution of potassium dichloride in water. You end up with the potassium chloride in water. It's not only aqueous, you have potassium ions surrounded by molecules of water and chloride ions surrounded by molecules of water. So you end up with a more disordered state. So even with an enthalpy which is not favorable for the reaction to be spontaneous, the increasing entropy is good enough, is large enough that allows that the process to happen. And in the composition of nitrogen oxide, it does not convert. It says results in a conversion of a solid to a gas. No, it results in the conversion of 1 mole of gas to 2 moles of gases. So you have 2 moles of gases rather than 1. So that's again more molecules of gas, more microstates, and increasing entropy. And it's large enough that even if the reaction is endothermic, even if initially that reagent will not react, it's enough that entropy is enough to compensate for that, and the reaction happens spontaneously.